All right, so in the last video we were studying this ideal I sub fa that was all of the polynomials that a is a root for, all the polynomials satisfied by a. And what we discovered was that if you chose any of least degree, then all the rest of them are just multiples of that one. And so this corollary at the top is going to tell us, don't just choose any of least degree, choose a monic one of least degree. There's only one of those choices, and then somehow will help us describe all the rest of them. So let's remember that word monic. That meant the coefficient of the highest degree term is 1. Okay. Sometimes that's called the leading coefficient because often when you write polynomials you start with the highest degree. Like when we write quadratics, we often like to write ax squared plus bx plus c. But because of the lens that we've been viewing these in, starting with rings and then coming to polynomials, I've been writing them in the opposite order where I start with the constant term and build up from there. So this leading coefficient is the coefficient of the highest degree term, and it's 1 if we call a polynomial monic. All right, so what the corollary says is there's only one of these things, that if you choose a polynomial of least degree, there's only one that's of least degree and monic. And so we can see this, so if we say something like, suppose p of x, which is f0, f1x, dot, 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 up to fn x to the n, is of least degree in IFA. Then, if we want to know what's the monic one, all we do is divide by fn. And that's it's monic and least degree. And that's the only one. All others are going to be multiples of that because that's one of least degree. All right, so once we know that there's only one of these things, then we can define it. We can give it a name. So the name of it is the minimal polynomial of a over f. And we squeeze all of that into one little abbreviated name. M subscript f comma a is the minimal polynomial of a over f. Okay, and this sounds really complicated. There's a lot of notation and a lot of machinery we built up, but this is something that is somewhat natural and you'll get very used to it. So for example, if we want to think about what's the minimal polynomial over q of the square root of 2. It's a polynomial, so I'm going to write it as m of x, and these subscripts q and root 2. So I'm supposed to find a polynomial. Root 2 is supposed to be a root of it. It's supposed to have smallest degree possible, and it's supposed to have coefficients from the rational numbers. So these are my field of coefficients. And so you might have already jumped to this. The polynomial is x squared minus oops, that's totally wrong. X squared minus 2 is my polynomial. That has rational coefficients. Root 2 is a root of it. And it's the best one I can do. So I cannot find a linear polynomial that root 2 is a root for. I know that because this is irreducible over q because root 2 is not in q. If I wanted to factor this, it would be in linear terms. So it would be a product of two linear terms. X minus root 2 times x plus root 2. But root 2 is not rational, and so that factorization is not valid over q. Okay? All right, but the q is important there because if I ask for m sub r root 2, this is the minimal polynomial of root 2 over the field r, then this time I can factor. And so my minimal polynomial now is just x minus root 2. Okay, that has coefficients in r. root 2 is a root of it, and there's not going to be anything of smaller degree that root 2 is a root of, because that's degree 1. A couple more examples that might help. So the minimal polynomial over r of I, where I is that I squared is -1, I is the square root of -1. If I want to use real coefficients and I want I to be a root, the best I can do is x squared plus 1. So it's a degree 2 polynomial, and it's monic. If I allow myself to have complex coefficients, then I can use x minus I as my minimal polynomial. So again, the idea here is I know this is minimal because I can't factor over r. On the other hand, when I'm allowed to use rational coefficients, I can factor. And so this is minimal because it's of degree 1. All right, one more example. So if we were going to take the minimal polynomial over q of the cubed root of 3, you might guess that the cubed root of 3 is the root of x cubed minus 3. And that's correct. That's our minimal polynomial. But the question that you should ask is, so this is a degree 3. Is there anything smaller? So can we reduce this? Can we factor it? Okay, so that's a lingering question. Cubed root of 3, it seems like my minimal polynomial should be x cubed minus 3. So we want to, if we want to argue that that's correct, we want to say that's irreducible. So one of the homework assignments will be reading through a proof of this, trying to follow those steps, and then reproducing it with some other examples. All right, before we wrap this section up, our big result of the chapter is this theorem. So I just want to read through this theorem, and then again, as part of homework, you'll be proving this. So we now have all the tools we need, and the proof is actually not too bad. So you're going to be able to work through it yourself, filling in some steps, and then we'll be ready to turn to geometric constructions, which is pretty interesting. All right, so here's our theorem. K over F is a field extension, like we've been seeing. A is an element of K, and it's algebraic over F. So the first part of this theorem doesn't rely on the minimal polynomial piece of this statement at all. It's the other version of the other direction of our big proof. So if A is algebraic, then the ring F adjoin A is actually a field. Okay. So that's the other half of the proof that we started this chapter with. Part 2 is, if the degree of the minimal polynomial is n, then in fact the degree of the field extension fa over f is n, and moreover we know a basis for fa over f. So this proof is not too bad. And it all is kind of hinging on, if A is algebraic, it's the root of some polynomial. The smallest degree polynomial that it's the root for gives us the degree of the field extension. And that's going to be really important to us in Chapter 7.